To horizontal asymptotes. In Math 20, when we do reciprocal functions, we talk about horizontal asymptotes just briefly. And basically what I tell you is that it's the relationship in terms of the degrees matched up against each other. So for example, their degrees is essentially 1, or they cancel each other out. So since they cancel each other out, it's going to flatten out at 1, because x squared over x squared is kind of that leading coefficient type of deal. So x squared over x squared is the leading coefficient. So this thing's essentially growing at essentially the same rate, okay? Because the x squareds kind of make the constants irrelevant, okay? Because if I put, as you can see, we put really big numbers here. That's how far apart they are. So it's not a very big deal. And so you can see that on the next picture here, that creates the horizontal asymptote of this. So it never goes underneath 1. Okay, so again, it's from the top 2 degrees here are both the 1x squared over 1x squared essentially makes it approach 1 as its asymptote. Okay, so that's what we're kind of looking at today. So from the table in the graph, we see that the values of f of x become closer and closer to 1 as x grows larger. In fact, it appears by taking x large enough, we can make it really close to 1, which indicates the type of behavior. Okay, so we indicate this type of behavior by writing limit as x goes to infinity. So what happens is we actually use limits to infinity to help us determine horizontal asymptotes. Because you may say, well, we've already done this. You're exactly right. We have done this. If you do infinity to, that's what we did. We said you take the leading coefficients of the highest degree. So in this case, it's essentially infinity over infinity, which is the same over same, so you still get 1. Okay, so that's what creates the horizontal asymptote. Does that make sense? So we're using stuff we've already learned to figure out horizontal asymptotes. So again, we say y equals 1 is the horizontal asymptote, which I showed you the picture. Similarly, we can see the large negative values. So for the large negative values, it's not a problem because of y. Why is large negative values not a problem? Squaring, right? So squaring it's not going to change, so therefore it's going to be still positive. Okay, in general, we define a limit to infinity by writing limit as x goes to infinity equals the limit. If values of x can be put arbitrarily close to L by taking what you need, so getting really close to it, it can give you essentially what it's approaching. That's just the idea of testing numbers around what you're looking for. Okay. Okay, again, one thing just to keep in mind, infinity is not a number but an expression. It's a way of how we write going on forever, but again, it's not countable. So we won't ever, don't think that infinity is a value, okay? The limit as f(x) approaches infinity is L. So which L is called the horizontal asymptote. So this is just pretty much going through the fact that if we do from x to infinity and x to negative infinity, that will pump out our horizontal asymptotes in terms of what we expect them to be. All right, so this one's kind of been overkill. You guys get it? It's 1. So here's a couple. So this is where it gets interesting, and this is where we have to kind of look at some end behaviors. So you can kind of see that first one there. As limit as x goes to infinity, what is the horizontal asymptote? It's this red line here, right? But you have to understand, it's as it goes to infinity. So that's not the asymptote going to negative infinity. That will happen. We will get stuff like that where it'll go up and it'll tail off. Okay? Same thing here, going to infinity. This isn't approaching it this way, but it's approaching it this way. So it has horizontal asymptote in that direction. So again, let me get to it. So see right here, at positive infinity and positive infinity, they have a horizontal asymptote. But negative infinity, they don't. See how it's just going straight down? That doesn't have one to negative infinity. It's not approaching anything here to negative infinity for a horizontal asymptote. Looks like this is approaching a vertical one, though, doesn't it? Okay. This here. Okay, so we will talk about ones like this where it's going to go up and down, and it's going to keep kind of hopping back and forth. That is approaching something. So we'll talk about that when we get to them. This one here, to negative infinity is good. Positive infinity, no. That's why that's to negative infinity. To negative infinity, okay, it goes up, and then it kind of stays on top. So that's a possibility. And then from negative infinity and positive infinity, this one's approaching a number, and then this way is approaching a different number. So L and M signifying 2 different horizontal asymptotes, which is also possible. So this is just kind of like an overview of different things that you could see. And we're going to learn how to find those. Yep. So it's still approaching, so by definition of limit, it's still approaching something, even though it's flip-flopping, kind of the idea of like a positive, negative, keeps flipping. So that's probably going to be like some type of odd function that is. This one? Yeah, so think about where it's, this infinity kind of means where it's ending to the right, and this one's ending to the right as it's approaching the horizontal asymptote. But to the left, you're right, there isn't one. Okay? These are just some things to think about. If you're saying, aren't these just easy parabolas? Aren't these just easy hyperbolas? Okay, there's going to be different. We're dealing with a lot of different functions in this unit with curve sketching. Okay? So just, I guess, in your mind, just understand these are possibilities, opening your mind up a bit here. Okay, so let's look at the first example. And all we're going to do is we're just going to kind of understand what it's asking. So for example 1, we're finding the limit as x goes to infinity for 1 over x, and limit as x goes to negative infinity for 1 over x. So when x is really, really large, okay, so if I get a really, really big number in here, what's it approaching as a value? 1 over 1 million. 0, right? So this one would be 0. Is that vertical or is that? That would be horizontal. Right. It is vertical too, because 1 over x is a hyperbola, so you're right. We got 0 for vertical. Yeah, this picture, remember, 1 over x is this right here. Let me see here, -1. It's this picture here. That's what 1 over x is. Yeah. So yes, vertical is 1, but what's also, vertical is 0, sorry, but a horizontal is also 0. Okay, so limit as x goes to negative infinity, even though we're going negative, it's still approaching 0. Because negative 1,000,000, 1 over negative 1,000,000 is a really, really, really small negative number. Okay, so this one is also 0. Okay, any questions there? Okay, so I mean, it's that simple. We've already done limits, so again, it's not confusing in the sense we've done limits before, and we have done limits to infinity. You usually know that when taking limit to infinity is what establishes your horizontal asymptote possibilities. Okay, so there will be harder ones as we will discuss. Okay, so we already have that. All right, I think I have. Okay, so 7 properties of limits that were stated in section 1.2 are also valid for doing this, which we understand. And if r is a positive rational number, then, so essentially for us, we just had 1 over x to the 1, right? So anything where this is essentially all this is saying, whenever the bottom is growing faster, it's going to be 0. That's all that's saying. Whenever the bottom is growing faster, it's going to be 0. Okay? And then same thing for negative infinity. Okay? And we already actually did that. Okay, I just want to, sorry to beat a dead horse here, but please understand what we're talking about. I'm talking about, as we go to infinity, we're talking about really large numbers. If it's a stationary 1 or something smaller on top and we're getting really big on bottom, it's a small number over a big number, which in fraction sense means a really, really small number. Okay. All right, so let's look at this one. You'll see how easy this can be. So, evaluate this. Limit as x goes to infinity for 4x squared minus x plus 2 over 6x squared plus 5x plus 1. Give you a second here to think about it. The problem should take about 20 seconds. Okay. If you're just getting settled in or you just got here, we're just doing limits to infinity because limits to infinity establish our horizontal asymptotes. We've already done limits to infinity, so that's the good news. But just to help you out here, irrelevant. We don't care about that. I only care about my biggest degree. And they match up. Does one grow faster than the other? Like what I'm saying is, was one x squared? They're both x squared, so they both grow the same speed. So your answer is 4 over 6, which is 2/3. So you have an asymptote at 2/3. On this one is what we're expecting. Okay, yep. No. Oh, on the bottom, yes. If it's x cubed in the bottom, that means the bottom's growing faster. and that means that it would be 0. If x cubed's on the top, that means the top's growing faster, and that would be infinity, which we don't have, that means nothing to us. Okay? But yes. Okay? All right, so find the horizontal and vertical asymptotes of the function here. So go ahead and try to do this quickly. I will pause the video. You have vertical from yesterday, see if you remember, and then horizontal from today. Okay. All right, so let's talk about horizontal first. So horizontal first, remember we're going to do limit as x goes to infinity. So of x plus 1 over x minus 2. Again, these are irrelevant. You have x over x, so we're going to get 1. So y equals 1 represents our horizontal asymptote. Try to leave a spot in the bottom right here so we can sketch it. Okay, so remember, we look at the critical values in a way, and maybe critical values is the right word, but we know 2 is an important value. We want to look and see what it's doing at those values. So this is where we did yesterday. We did limit as 2 from the right and limit 2 from the left. And so we look at those, and we just kind of see what's happening. So we're picking numbers really, really close. If you do that, you're going to see that from the right, you're going to get infinity. Okay, so what I mean is that if I do from the right means like 2.1. So if I do 2.1 right here, 2.1 minus 2 is 0.1. Remember I told you if it's a number smaller than 1, it's going to make that value bigger? So just to show you what I mean there, 2.1 plus 1 is 3.1 over 0.1. That value is 31, right? Just move the decimal over 1. So you see these are getting bigger. So this would be infinity. It's going to infinity. So at that spot, it's not going to cross 2. It's going to shoot up next to 2. Okay, well, how about 2 from the left? So like 1.9. Is that going to be a negative? Yeah, because it's going to be negative 1.1, and that's still going to be positive. Okay, so negative infinity. Any questions with that? Yeah.
Do you have to check with limits, or because it's on the bottom and factored, you can't just say it's for sure if there's no?
Yes, it's because it's already factored. Yeah, we're kind of overdoing it, but yes. But this tells you which way the graph's going.
Okay.
So I don't know off the top of my head, but you might.
No, definitely don't.
Okay. All right. So we know 2 is a vertical asymptote. So I'm going to put my dotted line here. Use a different color here for dramatic effect. So there. Wow, that is not a straight line, but it's all right. Okay. And then I know I have a horizontal at 1. So that's kind of where my sections are. Do you remember how things got sectioned off a bit in Math 20? That's kind of what my sections are. What I mean by that is I see I got 1, 2, 3, 4 sections. So we know that if coming from 2 from the left, we know it's going to negative infinity. That means I can't cross this line in this example. So it's essentially, this is the only thing I can draw that would make sense to that labeling. So I'm coming to 2 from the left, and it has to get to negative infinity. I have to be in this box, if you will, and I'm dropping at that asymptote. Conversely, this one's going to have to be up here, so it goes up. So this represents that graph. That's how you can draw that without your calculator. You can still, if you remember, you can still use invariant points. You can still use those things if you remember what that is at all. But we can talk about that another day. But, okay. All right. A couple things I put on here. The x-intercept. 0. So x-intercept is at 1 or negative 1. Nope, 1. So no. X-intercept from the top 0. Sorry, the x-intercept is at negative 1. So I wonder if my graph's off here. Let's see. If I do, let's see, if I put negative 1 in here, I get 0. If I put 1 in here, 1 plus 1, 2, yeah, so my graph's off. Should be falling earlier. So it should be more like this. Okay, and yeah, that makes sense because the y-intercept is -1/2. Yeah, that makes sense. Okay, so sorry, just whenever you're finding the x-intercepts, you'll make y 0. How do you make this guy 0? The top needs to be 0. Okay, because if the top's 0, then everything's 0. Okay, to find the y-intercept, we make x equals 0, and then see what happens. 1 over -2, so that's -1/2. So that's why it goes through right there. It's a little bit more accurate. Okay. We're kind of talking about things. The next 2 lessons, we will be doing all of them. We'll do in concavity and all those things that we'll be able to make these sketches. Okay, so we got that. All right, example 4. All right, so find the horizontal and vertical asymptotes of that function. Okay, so you will want to factor. Okay, I'll pause it. We'll see how you do here. I don't know if you try to sketch it or not, I'm not sure, but this is an example where you're going to see that the asymptote, if we get an asymptote, it sounds kind of weird, but the asymptote can still get crossed in certain intervals. But on some intervals, it will not be able to be crossed. Okay, so if you look at this graph, I'll just kind of do like the spoiler alert a little bit here, but this graph looks like this. That's what this graph's going to look like. So it definitely has an asymptote. My one there's a little high, but it still does. If you got horizontal asymptote 0, you're still right, even though that cross is there, because it's talking about the end behavior, to infinity and to -infinity. It's still not crossing that. Okay, so just kind of understand that it's not the end-all be-all, that it will never be crossed. Just kind of get that in mind. It's in your book too, a little bit better picture than I drew, but you can kind of see that. So let's do the horizontal asymptote first. So remember, horizontal asymptote, if we do, we'll factor this first. X minus 3, x plus 2. It's easier to take the limit here because the bottom is growing faster than the top, right? The bottom's growing faster than the top. So that's going to be 0. Okay, and again, it doesn't matter if it's negative, because it should be a really, really small negative. Okay, so your horizontal asymptote is at 0. Or y equals 0. Okay. All right. So then we see that after we factor, our vertical asymptote spots we need to look at is 3 and -2. So we need to do 4 limits here. 3 from the right, 3 from the left, -2 from the right, and -2 from the left. Okay, so if I try something bigger than 3, I won't write this, but this is what would be in here. If I just try something a little bit bigger than 3, it's a little bit easier to put it in here so you can see what's happening. If I do like 3.1, okay, well 3.1, that's 0.1 times 5 is going to be small. And it's going to be over a 0.1, so it's actually going to be infinity. So again, if I put 3.1, that's a number to the right of 3. I put them in here and here. So that would give me 3.1 on top. That would give me 0.1 times 5.1, which would be 3.1 over 0.51, which you see this is a smaller number again, so it's getting bigger. Okay, 3 from the left would give you still infinity. Oh, no, sorry, -infinity. Because we have the same situation, but a -0.1. And that explains on the picture. So at 3, so 3 is this spot. If I'm coming to 3 from the right, it's going to infinity. Okay, if I'm coming to 3 from the left, -infinity. That's why this guy's wrapping here. Okay, so 3 from the right, going up, 3 from the left going down. All right, so the negative 2 to the right, it's going to be the same thing, but we can also even look at the pictures to have it up here just to kind of confirm. But negative 2 from the right, that would be negative 1.9. So you put negative 1.9 in there. It's going to get you a positive and a negative. So from the left, I have it negative infinity. That's here. And then from the right, oh, sorry, this is the right. My bad. So negative 2 from the left, there. From the right, there. Positive. Okay, we've got one last thing to cover, and that's it. With 2 examples. Okay, any questions on that? So again, horizontal asymptotes is the relationship of the limit to infinity of your top and your bottom. What's growing faster? If they're growing the same, it's the coefficients over each other. Vertical asymptotes, you need to know what the bottom or how we can get non-permissibles of where your graph can't be, and then you go from there. Oh, I did put the better picture up, but this is the better picture than my drawing. Okay. All right, so infinite limits at infinity. So we use the notation of x to infinity of fx equals infinity to indicate the values of fx become large as x becomes large. It's just basically what we were just doing. You know, this right here, as I go to infinity, the answer is going to be infinity. They just grow together. Same thing here. This would be as it goes to negative infinity, I get negative infinity, positive infinity. Okay, so you can see that's what these are saying. So limit as negative infinity of x squared stays positive because x squared is even, so it goes up. Right here, the positive goes up. Positive still goes up here, but negative for an odd can actually go down. That's all that is. Okay? All right, so what would this one be? Limit as x goes to infinity for x to the fourth minus 1x. So this is where like it gets like kind of tricky in a sense that I said we can't have a value, right? But we know that like we can write this in a way, you know, we can manipulate this a little bit to make it look like this if we wanted. And then we know that with our, we can write with our limit properties, we can break it up. But at the end of the day, it's just going to be infinity. Okay, because when you look at, for example, think about the line x. The line x is just a simple linear line. As it goes to infinity, it's going to be a relationship to infinity. X cubed, we just talked about. Doesn't really matter the minus 1, just move down 1. As I go to positive infinity, it's going to be positive infinity as well. So these are both going in a positive infinity way. So therefore, the answer would still be infinity. Okay. So all I'm telling you is that like it's best to write it this way, because if you just have this, you can't just plug that in and get infinity minus infinity. That won't tell you anything. That's what I'm trying to tell you. Okay, you need to look at it in terms of how the pieces of it with your limit properties. If you're wondering why I was doing that. All right, this is the last example. Sketch the graph of y minus 3 squared, y plus 2, 1 minus x by finding its intercepts and its limits as x goes to infinity and x goes to negative infinity. Okay, so let's start with the first thing. Let's do the y-intercept. That's the easy one. How do you find y-intercepts? You just make x 0, right? To find y-intercept, make x 0. To find x-intercepts, make y 0. So we're just plugging zeros in here. Whoops, not plus. Multiplied. So that's what you have when you plug zeros in. So you're going to see that your y-intercept would be 9. It's going to be 18. Okay, so we'll log that. On the next page, we'll kind of sketch a graph. We'll get all the stuff that we need here, and then we'll sketch the graph last. Okay, how about your x-intercepts? Well, they gave it to you nicely, right? Like, we know how we can make y 0 here. 3, -2, and 1. Just like solving by factoring, right? That's already factored, so we already have those values. So your x-intercepts are 3, -2, and 1. Okay, so now if we do the limits, so you guys haven't been saying much, I've just been up here talking to myself, but when I say limit as x goes to infinity, what does that for sure tell us about the graph? Let's talk about what that means. Yeah, it can, but in terms of like if you're graphing this, and like you have information, and I say your limit to infinity is infinity, what does that mean about your graph? Yeah, so the word I'm kind of looking for, it tells you the end behavior. So if you say limit as x goes to infinity, however your graph ends to the right, it's ending up. It's going to be going up forever if you get infinity. If you get negative infinity, that's telling you the graph is going to end angling downward. So it tells you what's happening on the ends, and then we use those intercepts and stuff to figure out what's happening in between to kind of get a rough sketch. Okay? Kind of think about sectioning it. You'll see what I'm talking about with concavity tomorrow. But anyways, just wanted you to understand. This is essentially telling you the end behavior. All right, so limit as x goes to infinity. So how can I figure that out? Well, we can figure out what's happening by, okay, infinity, a really large number. A really large number squared is what? Like positive or negative? A really large number plus 2, is that positive or negative? A really large number subtracted from 1. Positive times negative, so what's that do? It's a negative infinity. That's what's happening. It's fallen. Does that make sense? And then do the same thing for your to negative infinity. So that's still going to be positive. Negative. So we're doing positive, negative, positive. So, yeah. So then we get negative infinity for both of them. So that means this graph is ending downwards for both. All right, so if we take that and we kind of plot these points, I think I can actually squeeze it right here. Okay, so I'm going to plot everything I know. I know my y-intercept's 18, so we'll say that's 18 right there. Okay, I know that my intercepts are 3. And I know it's also 1 and -2, right? Yeah. So there's my intercepts. Now here's the thing that I kind of know, or I do know. I know these are my outside intercepts. It's doing that, right? Because we know the end behavior is negative infinity. And now you can kind of piece it together. Well, I know I have to go through the y-intercept, and the y-intercept's before 1. So I have to go kind of essentially like this. Like something like that. That's essentially what it has to do. Okay, and that is correct actually. Like, and it's going to, in this case, you're like wondering, well, how does it do that? It bounced. We know bouncings are possible. Okay, so it essentially came up, hit that, and bounced right off. Okay. So that's the graph we just kind of figured out with the information we were given. Okay, we'll stop there.